We have a seminar today from Professor Lucy Campbell. She's coming to talk to us about mathematical studies of atmospheric wave interactions. She's from the School of Mathematics and Statistics, Carleton University in Canada. So let's give her the hearing. And there are some other people, Prof, online, and there are some other people physically attending here. So what we will do is that we will allow you to present your talk, and afterwards we will ask for questions. And we might also have some questions in the chat. We will also follow through with that one. And then from there, I believe that we're going to enjoy your talk. Welcome to Wits University in Johannesburg. We had hoped you'd have been here physically, but you are here somehow with us. And then in the future, we hope you'll be able to come here physically. Welcome, and take us through your talk. Thank you.
Okay, thank you very much for inviting me to for all these different options, and I'm glad at least Zoom works for us to be able to connect. So I'm Lucy Campbell from Carleton University in Ottawa, the capital of Canada, and I'm going to be talking about mathematical studies of atmospheric wave interactions. So I understand that I'm speaking to a diverse audience, including mathematicians and possibly some atmospheric scientists and maybe others. So I'll give a very general talk where I'll start with some very basic definitions and background, and then give a short overview of some of the things that I'm doing in my research involving applied mathematics applied to geophysical fluid dynamics. I hope that at some time in the future, I might be able to be there in person and meet some of you. I've never been to South Africa before, so I was just saying to Tama at the beginning that I'm half Ghanaian. My mother was from Ghana, so I did live part of my life in Ghana. That's the closest I've been to South Africa in my life. So I'm going to be talking about my research in geophysical fluid dynamics. And so, of course, geophysical fluid dynamics is the study of gases and fluids, so gases and liquids, so fluids in the Earth's environment. And we are in geophysical fluid dynamics, we are interested in the movement, the dynamics of the fluid. And the fluid could be a gas or a liquid. So in the context of geophysical fluid flows, that means air in the atmosphere or water in the ocean or in any large body of water. So as we see in our pictures here, I'm also half Barbadian. So my mother was from Ghana, my father was from Barbados. So this picture is from a picture of a beach in Barbados, photo that I took the last time I was there, way back in 2016. And this other picture here is a picture of the clouds over Ottawa 2 years ago, big photo that I took. I'm always looking out for waves when I'm out, and whenever I see them, I stop quickly to take photos. So geophysical fluid dynamics involves how the atmosphere and oceans and other large bodies of water change over time, over the short term and the long term. Short term, which is modeled by or described by the weather, and long term, which is described by climate. Now, I'm a mathematician, so I use mathematical models to study geophysical fluid dynamics. And of course, fluid dynamics is described mathematically using the laws of conservation of mass, momentum, and energy from physics. So we have our equations that are derived from those laws. For example, the law of conservation of momentum, which we are all familiar with, Newton's second law, the force is equal to the force acting on a body is equal to the mass times the acceleration. It's the rate of change of momentum, so mass times velocity. So that gives us the mass times the acceleration. So our force is the mass times the time derivative of the velocity. And in the context of fluids, we consider the force per unit volume. So instead of mass, we would have the density, the mass over the volume. So force is mass over volume times dv dt, or density times dv dt. So that leads to, in three-dimensional space, leads to the well-known Navier-Stokes equations. In 3D, for example, in rectangular coordinates, writing things in rectangular coordinates with a fluid velocity with components, say, u, v, and w, we end up with a set of equations like these. Now, of course, we could use any other coordinate system depending on the problem that we are interested in. But in rectangular coordinates, we might have the density times the vector written as three equations of du dt. So components du dt, dv dt, and dw dt. And then on the right-hand side, whatever forces are acting on the fluid. Now, in our set of equations, we are using this notation of capital D dt, which represents the rate of change of the fluid following a fluid particle. This is what's called the Lagrangian derivative or total derivative. So it involves the partial derivative of the quantity, fluid quantity, with respect to time, and then plus the product, the dot product of the velocity vector uvw with the gradient of the quantity. So the partial derivatives with respect to x, y, z. And so that gives us our Lagrangian or total derivative. So these are acceleration terms in our fluid equations, the density multiplying these acceleration terms. And on the right-hand side, we have our forces. Now, the forces in the context of the atmosphere, the forces could include a pressure gradient force. So these represented by these derivatives of the pressure P with respect to the different variables, a gravitational force which would act downwards. So in my context here, it only has a component in the Z direction, which would be our vertical direction, and other forces. In the context of a fluid on the Earth, we have the Coriolis force as well, which results from the rotation of the Earth. And so those would be our, of course, there could also be a viscous force describing or resulting from the effects of viscosity in the fluid, that friction within the fluid. And other forces are possible depending on the context we are studying. So these are the equations for the conservation of momentum, and we might have equations for conservation of mass and energy as well. And so, of course, these are partial differential equations which represent the rates of change of the properties of the fluid, such as u, v, w, velocity components, pressure, and so on, with respect to space and time. In this case, the space is represented by three rectangular coordinates. And our mathematical problem is an initial boundary value problem. So given the current state of the fluid flow, now at time t equal to 0, our reference time, in some specified region in space, we want to get, and some information given about the flow on the boundaries of that space. We want to solve the equations to find out the state of the flow at a later time within that region. And of course, that's what we do in weather forecasting and climate modeling. We have some information about what's happening now or what happened in the past, and we are using that to predict what will happen later based on information, spatial information. And so in the kind of work that I do, I use numerical methods, discretizing the equations and using solving numerically. But I also use analytical methods. So like asymptotic analysis, perturbation methods, multiple scaling, and so on. And in order to use analytical methods, we don't have exact analytical solutions. We almost never have exact analytical solutions for whatever it is we want to model. But we simplify by neglecting whichever terms are less important in the context that we are interested in. And then we find approximate solutions using some of the methods that I just mentioned. I almost always use both analytical and numerical methods. Like I start my study by using analytical methods, get some approximate solutions to simplified versions of the problems, and then use those for verification of the numerical results when I start to do the numerics, and also for interpretation of information from observations and measurements that I can compare with my results. I don't go out and take measurements myself. So I'm really a mathematician, not a physicist or engineer who is going out, or an atmosphere meteorologist who is going out to take measurements. But I do compare my results with published results obtained from observations and measurements. So I'm particularly interested in waves in geophysical fluid flows, as I just mentioned. That's why I like taking photos of waves in clouds, like what you see in my background. So waves in geophysical flows, I'll just mention a few different types of waves. So we all know that there are waves on the surface of water. There can be waves on the surface of water, but there are also waves in the atmosphere, and those are the ones I'm most interested in. And an example would be gravity waves. So gravity waves are waves that result from the combined effects, opposing effects of the gravitational and buoyancy forces. So the gravitational force acting downwards and the buoyancy force that allows objects to float acting upwards. And gravity waves can result when there's fluid flow over some obstacle, like what's shown in this diagram here. And the competing effects of the forces acting downwards and upwards can result in an oscillation of the fluid particles. Now, there are different types of gravity waves. They are all relatively small scale. And when I say small, because I'm interested in what happens in the Earth's environment, small scale for me means small relative to the size of the Earth, but they may be large relative to us standing on the surface of the Earth. So wavelengths up to about 1,000 kilometers maximum. Now, there are different types of gravity waves. There are surface gravity waves, which are actually waves on the interface between two fluids. So those are the waves that we see on the surface of the ocean, for example, or any body of water, on the interface between the atmosphere above and the water below. And then there are also internal gravity waves which occur within the interior of a fluid. For example, within the atmosphere or within the ocean. So those would be like these waves in the clouds you can see here. You can see these lines, darker and lighter regions in the clouds, the crests and the troughs of the waves in the clouds. And so these are internal gravity waves, and those are the ones I'm more interested in. Although there's a very large body of work on surface gravity waves as well, but I have devoted less attention to those. So internal gravity waves are often observed above convective clouds or above topography, like what I showed in that diagram earlier. This is a picture of gravity waves in over marine stratocumulus clouds over the Indian Ocean. So a picture I took from the NASA website, and you can see the lines here, crests and troughs of the waves. And this is my picture you see in my background, gravity waves over the Central Experimental Farm, which is a scientific research farm within Ottawa, quite close to where I live. And you can see these look just like the ones in the picture. Now, there are other larger scale waves as well in the atmosphere. For example, planetary Rossby waves, which are waves that are generated primarily by the effects of the rotation of the Earth, the Coriolis force. Gravitational and buoyancy effects may play a role in the development of these waves as well, but a much lesser role. And these planetary Rossby waves, they are called planetary because they are on the planetary scale, and Rossby because they are named after a meteorologist, famous meteorologist from the past, Swedish meteorologist called Rossby. So these are planetary scale waves, and this is the scale of the waves relative to the size of the Earth. All my pictures are from the Northern Hemisphere. Unfortunately, I don't have any information or pictures from the Southern Hemisphere, but those of you in atmospheric sciences, I'm sure are familiar with all these things I'm talking about in your context in the Southern Hemisphere, perhaps. So maybe that's something I need to start looking into if I have hopes of one day coming to visit all of you over there, down in the south. So they appear as large-scale meanders in the jet stream when we see them in the Northern Hemisphere. So like these two pictures here, taken from the Environment Canada website. This is the jet stream over Canada. This was an earlier picture from I took downloaded from the website in January of 2022. So this is in winter, so colder temperatures. You can see the blue show negative temperatures, negative Celsius. Negative values in degrees Celsius. And then this is a more recent picture from July of 2024 this year. So the red and orange are higher temperatures. So this is in the summer. We have quite extremes in temperature here in Canada, going from -30 up to 30 over the course of the year between winter and summer. So we see these red arrows show the kind of oscillation I'm talking about. An example of a context in which weather is often influenced by planetary Rossby waves in Canada is the polar vortex. So the polar vortex is a vortex which looks like this, kind of in this diagram, around the North Pole. Again, I'm giving an example from the Northern Hemisphere, because those are what I've been looking at. So this is an example of a stable polar vortex, a vortex around the North Pole, and the polar jet stream. And then when the vortex becomes unstable for whatever reason, maybe larger amplitude, and then it breaks apart due to some nonlinear effects, then the cold air from the vortex pushes cold air south, and then the warm air moves north, and there can be an oscillation like this. Now, this happens quite frequently in Canada during the winter, or in the Northern Hemisphere during the winter, where we might sometimes have situations where there is very cold air over one region, some region in the Northern Hemisphere, and then at that same level, same latitude, going east or west, there's much warmer air, unusually warm air. So we might have a situation where, for example, in Canada, at a given time, it's really cold, but over in Europe, it's really warm. Or sometimes the opposite, when we have unusually warm weather in Canada, warm to the point where it's raining and so on in winter rather than snowing. But it's unusually cold in Europe, which is a problem for them because they are not so used to the kind of cold weather that we in Canada are used to. So that's a common effect of a very large-scale planetary Rossby wave that we are familiar with in Canada. Now, so there are different types of waves in the atmosphere, and the wave interactions affect the general circulation of the atmosphere. So in this diagram here, there are in the tropics, this is the equator, the North Pole, and the South Pole. So taking the Earth and opening it out into a rectangular region, taking the atmosphere around the Earth and opening it up as in a rectangular region. So this is the vertical coordinate, altitude. So in this diagram, we see different types of tropical waves around the equator. So those include gravity waves, inertia gravity waves, Kelvin waves, and Rossby gravity waves. So various other types of waves. Rossby gravity waves have the Coriolis effect, as well as the gravitational and buoyancy effects. Kelvin waves are waves that occur near a boundary. So there are different tropical waves, and then there are also the planetary scale waves I just talked about in the Northern Hemisphere. In this picture, they are basically saying that there's nothing going on in the South, but I'm sure that's not true. It's just that the picture was made maybe by people from the Northern Hemisphere who don't pay attention to what happens for you guys down in the South, which is something I need to learn more about myself. So in addition to these, there are even smaller scale waves such as vortex-Rossby waves, which are waves that are outward propagating disturbances within a tropical cyclone. So these are like hurricanes and other types of cyclones. Within the hurricane, there might be some waves propagating within the hurricane. So these are much smaller scale waves, which result from the radial gradient of the vorticity of the cyclone, as opposed to the gradient of the rotation, the radial gradient of or as opposed to the effect of the Coriolis force, the rotation of the Earth. So all these different types of waves exist in the atmosphere. Now I'm interested in many different types of waves, and from a mathematical perspective, they are very similar. Although physically they are very different, from a mathematical perspective, they are very similar in the sense that the equations all start from the same place, laws of conservation of mass, momentum, and energy, but different forces and different parameters appear in the equations depending on what we are looking at. And of course, the domain for the mathematical problem would be different depending on what problem we are interested in. So for smaller scale waves, such as gravity waves or the waves, vortex-Rossby waves, are not always properly resolved by large-scale models because they may be smaller or on the same order of magnitude as the grid spacing in a numerical model. And so, of course, they can't be resolved in that case. So even now that computer power is much greater, and we are able to have relatively fine resolution numerical models, still some waves cannot be completely resolved. And so analytical studies provide us with missing information that can then be added to the large-scale model. So mathematicians like me would typically study and develop analytical solutions, do smaller scale numerics and so on, and that would give us some insight into what we need for the large-scale models. So in the perturbation approach, we consider each fluid quantity, so like the components of the velocity, the density, the pressure, and so on. Each of these quantities, say F total, being the sum of a mean or background quantity and a wave that's added on top of the mean, oscillation on top of the mean. Now, considering the wave to be oscillatory, we would usually say that this function F is some oscillatory and periodic function over some x interval, where x may be the coordinate, say, horizontal coordinate. So x is our variable. And in that case, we can represent the wave by Fourier modes, like sines and cosines. Let's say sine kx or cosine kx, where k is the wave number, and then a wavelength of 2 pi over k. We might consider a single mode, like e to the plus or minus ikx, or a Fourier sum, or a Fourier integral. And so that allows us to use Fourier methods for numerics as well. And we can take like Fourier transforms and so on. Now, with that representation, it means that whenever there are nonlinear terms in our equation, we will have products of different quantities, different fluid quantities, so the functions and products of the functions and their derivatives. And so if we have quantities that are represented by Fourier modes like these, then it would mean that if we have a product of two modes with different wave numbers, we would generate as a result additional modes whose wave numbers would be sums and differences of the existing ones. And so products of Fourier modes like e to the ikx and e to the minus ikx will of course give e to the 0 independent function terms that are independent of the variable. Those are 0 wave number components in our fluid, which even if not initially present, once the waves start to interact with each other, then they will generate a mean flow. So that's the wave-induced mean flow. And that means that although the waves may be small scale, when they interact in a nonlinear form, they generate a mean flow, which means energy and momentum from the waves being transferred to the large-scale general circulation. And so that's the effect. That means that waves have an effect on the background flow. Even when the waves are small, they might create large-scale effects. And also products of Fourier modes like e to the kx and e to the kx, e to the ikx and e to the ikx. Multiplying the mode with itself will give 2ikx. And then that will multiply with e to the ikx again to give 3 and 4 and so on. So we also generate higher harmonics, higher wave numbers. And these, of course, are smaller scale waves. So the wave interactions can give rise to a wave-induced mean flow and smaller scale effects as well. And the fact that there is vertical stratification in the atmosphere, the density and temperature change with altitude means that the wave amplitude in general increases with altitude. So, of course, when a wave has a higher amplitude, it has a greater chance of breaking, as we know from surface waves. So wave breaking and an effect called wave saturation can occur. Wave breaking can lead to turbulence. So when air flows over a mountain, and that generates gravity waves, internal gravity waves, which go up, the amplitude increases, and then the waves break, then that generates turbulence, which is why when we fly over a mountain, in a plane flying over a mountain range, we tend to experience turbulence. That's a common thing we experience in Canada when we fly west and go over the Rocky Mountains. There's also an effect called the critical layer, which occurs when the background or the wave phase speed is equal to the background, the velocity or the speed of the background flow. And then that leads to a phenomenon called the critical layer effect, which also leads to sometimes wave breaking and other wave mean flow interactions. Now, all of these type of interactions I talked about can be modeled mathematically by simplifying the equations to the point to make them tractable and then applying our mathematical methods. So I'm going to give an example of one of the many types of waves I've been looking at, which would be vortex-Rossby waves, what I mentioned a few minutes ago. I've looked at all the different types of waves I just talked about, planetary Rossby waves, internal gravity waves, and so on, over the past number of years in different contexts. Sometimes some of my grad students have worked on problems involving these different types of waves. So I've had a PhD student and a master's student work on vortex-Rossby waves over the past few years, and it's an ongoing topic of interest for me. So vortex-Rossby waves are waves that occur within a cyclonic vortex. And so a cyclone is a system of rotating fluid flow with sustained winds in the form of a vortex. This is an example, just a cross-section diagram showing a cross-section. So a tropical cyclone originates over the tropical oceans and is driven by heat transfer from the ocean. And then a hurricane is a tropical cyclone with a very high maximum wind speed. And I think we are all familiar with the general idea of a hurricane, which has an eye in the middle, a calm area with low atmospheric pressure, surrounded by an eye wall, and then which is a ring of very intense thunderstorms and wind circulation and very high angular velocity. So in this picture, we have an eye wall, and then secondary eye walls might develop around that with time. And the eye wall is a rain band, very high ring of intense thunderstorms. So for obvious reasons, it's important for us to be able to model hurricanes properly because of the very devastating effects they can have wherever they develop and in the regions that they pass through. Now, vortex-Rossby waves occurs outward propagating disturbances within the cyclonic vortex. So like in this case here, in this picture, we have a hurricane, and the red would be the eye wall. There's an outer eye wall, secondary eye wall, and there's a process called the eye wall replacement cycle, which is well documented, where there's an outer secondary eye wall develops and intensifies and then moves inwards to replace the original eye wall. Then another eye wall may develop on the outside and move in, and so on. And it's been shown that this cycle, which intensifies the hurricane or the cyclone, is affected by the presence of vortex Rossby waves within the cyclone, because of the fact that when the vortex Rossby waves interact with the background vortex flow, they can result in changes in the vortex, background vortex, just like what I said here, the wave-induced mean flow within the vortex. Now, the other issue is that vortex Rossby waves can contribute to what's called a beta gyre, which is where there's a secondary circulation develops in the form of a dipole, accompanied by displacement of the vortex called the beta drift. And it turns out that the presence of the waves within the vortex can have an effect, put some additional force, or increase the angular velocity of the background vortex and result in a displacement of the vortex. So that can contribute to the track of a tropical cyclone. So this is a picture from the Environment Canada webpage showing Tropical Storm Alberto. That was the first storm in the season this year, in the hurricane season this year in June. And for this hurricane, Alberto was followed by Beryl, which was an even more severe hurricane that affected all the islands in the Caribbean. I always follow the weather news in the Caribbean, because although I mentioned I'm half Ghanaian, I'm also half Barbadian. So my father was from Barbados, my mother was from Ghana, so I'm from both sides of the Atlantic. And although I live in Canada, I always follow what's going on in the Caribbean still. When I lived in the Caribbean as a child, and I do remember several hurricanes that affected us during the time that I lived there as a child. Way back many decades ago. So the beta gyre effect, understanding the beta gyre effect is important for accurate forecasting of the tracks of tropical cyclones. And in a mathematical formulation, the beta gyre effect results from the balance between the effects of nonlinearity that I just talked about and the rotation of the Earth, which affects the vortex. Even though the waves result from the rotation of the vortex itself, the rotation of the Earth also affects what's going on within the cyclone. Now so there's a lot of previous work on mathematical models for representing this beta gyre effect, but the previous work generally involves sort of linear equations, and they are not doing without a full asymptotic analysis of the nonlinear equations. So my approach is to do a weakly nonlinear study using asymptotic analysis and perturbation theory to try to understand the nonlinear effects, because it's only with nonlinearity that we can see how the waves affect the background flow. And so this was a problem that I looked at with a student, Ming Yao Chai, who is currently doing his PhD with me, but he completed his MSc Masters couple of years ago, and 3 years ago, and this was his master's topic. We haven't yet published this, but we will have to get around to doing that quite soon. So in this study, we make things very simple, well, relatively simple, in order to allow asymptotic analysis. Now, the next step after that would be to do numerics. And then once we are doing numerics, we can use a more realistic model. So the simplest model we can use to study vortex Rossby waves would be a barotropic model, which in this context, barotropic just means 2D, like a horizontal model where you're on a horizontal plane. Horizontal meaning on the surface, horizontal meaning parallel to the surface of the Earth. Now, of course, the Earth is a sphere. So what would that mean? But it means that we can make an approximation where we approximate our spherical atmosphere by a vertical horizontal plane. Now, in this study, we used asymptotic methods to find solutions, approximate solutions at different orders of the relevant parameters. So we start with our 2D version of the equations we had earlier, momentum conservation, and the simplified version of the continuity equation, the law of conservation of mass, simplified because we are on a horizontal plane, and so we are not including density changes in the vertical direction. And in this case, we have our viscous terms. the effects of viscosity, pressure gradient terms here, and the effects of the Coriolis force, and then our acceleration terms, and then our continuity equation, which is the law of conservation of mass. And because we are not taking into account changes, vertical changes at this point, we don't have to couple in the energy equation for now. So the Coriolis parameter is this F, which is 2 times the Earth's angular velocity times sine of theta, where theta is the latitude. And so latitude is measured like that, but along the curvature of the Earth. But we can consider a plane if we take a spherical Earth. Let's see if I can, when I bring my globe up too high, then my head face disappears because of my background, but you can see my globe. And if I take a strip around the globe and then open it up like what I've shown here, then I can get a rectangular domain where X will measure my longitude and Y will measure latitude. But of course, that can only make sense. It's only a good approximation if my my latitudinal distance, dimension of my domain is very small. Obviously, if it's too wide, the wide north-south direction, it wouldn't make sense. Okay, so we can take our strip, open it up, consider a rectangular region. We are going from some point all the way around back to that point, so X goes from 0 to 2 pi. We can approximate the Coriolis force by a constant, that's the F-plane approximation. But in order to have model the vortex-Rossby waves, we can take the next best, slightly better approximation, which would be a linear approximation, constant F0 plus beta times Y. So in that case, beta is the dF dy, the gradient of the Coriolis parameter in the latitudinal direction. This is a well-known approximation called the beta plane approximation. Once we have that approximation, then we have our equations written in 2D. We can define a stream function which is related to the velocity components u and v. For this analysis, we neglect viscosity. So the nu in the equations, these higher derivative terms are neglected. So that makes our equation now first order, but still nonlinear. And then we can combine the equations by taking the y derivative of the first equation and then the x derivative of the second equation and subtracting them. And we end up with a single equation which is called the barotropic vorticity equation. Now, the barotropic vorticity equation, you can see it's still nonlinear. It's got these products here, and the t derivatives, the subscripts here represent t derivatives. So this is the t, represent partial derivatives. So this is the t derivative of the Laplacian of the stream function, and then the x and y derivatives and so on. So we still have our nonlinear terms. We have our beta term, and we have our time evolving term. Beta is a small parameter in the context of hurricanes, because if we non-dimensionalize our equations, then the beta ends up being taking into account the orders of magnitude of the quantities we are studying, the angular velocity of the Earth, the radius of the Earth, the typical length and velocity scales of a hurricane, and so on. Beta ends up being a small parameter, small in the sense of asymptotics. So we can do asymptotics where we consider it to be a small parameter. And in this case, because we are looking at a vortex in a circular domain, we'll use polar coordinates. So the same thing I said earlier, the total of each quantity being the background flow plus the perturbation. And the perturbation is multiplied by epsilon, which will be our non-dimensional parameter that will tell us the magnitude of the wave relative to the background. And so this is our domain. This would be the eye wall of the hurricane. And then the waves and the vortex is in this annular region around the eye wall. And then the waves would be propagating in this region, propagating radially outwards. So plugging this into this form into our barotropic vorticity equation gives us an equation for the wave in terms of the background flow. So all the quantities with the bars on top are the background flow quantities that we know. And so in our equation, we'll have some terms involving beta, some terms involving epsilon, and then some terms involving beta over epsilon. And when we plug this into our equation and divide through by epsilon, we'll have the parameter beta divided by the parameter epsilon. Now, both of them are small parameters, but we are considering that beta is much less than epsilon. So the waves are quite nonlinear, but the beta effect, which is the effect of the rotation of the Earth, is small on the vortex. So the beta is small compared with epsilon, and so we can take gamma to be beta over epsilon and consider that also to be a small parameter. And so we'll start with, set it up as a mathematical initial value problem, have some initial vortex flow given by some function like some function of r, the radius, e to the ik lambda, where lambda is the angle. R and lambda are polar coordinates. And for mathematical tractability, we'll consider a wave that's of the form e to the minus constant r squared. So like Gaussian profile, decreasing like that as we go outwards from the center of the vortex. And so in 2D, it would look like this. So the initial wave profile looks like this. And then there's a background vortex flow that also takes that form, but we want to have the alpha, the constant in this exponential, to be much smaller than the mu, which is the constant in the wave, background wave, so that the vortex background flow decreases more slowly than the wave, and the wave stays contained within the vortex. So we'll have several small parameters: beta, the effect of the rotation of the Earth; alpha, which defines the radial scale of the vortex; mu, which will define the radial scale of the wave; and epsilon, which will define the wave amplitude. And we want the beta to be much less than epsilon. So when we do all that, we can do asymptotics, which usually involve, or in this case involves, starting with a perturbation kind of configuration, where we say we look for solutions that are in the form the leading order term plus powers of alpha plus a term corresponding to epsilon, and then a term that corresponds to the gamma and maybe the beta as well. So all these, the different parameters appear in the problem. Now the analysis is very complicated and was done by my student. We can take these and plug them into our equation, so get a leading order equation, solve that exactly, then take that and plug that back into the right-hand side of the next order of the equations, solve the next equation, and we can solve in a sequence like that. And we end up with this solution. And so I'll just say a few words about the solution and then show a picture of what the numerical results look like to wrap up my talk. So this is the psi here, I should mention, is the vorticity. So we are working with the stream function, but it appears as the Laplacian of the stream function, and the Laplacian of the stream function is the vorticity. So that's what this symbol is, psi. And so we solve for the psi, the vorticity, and it turns out to be this. There's the leading order solution, which is something very simple. There is an order alpha term, which is all this, plus a next order in alpha, higher orders in alpha. And then there's the order epsilon, which is the term, these are the terms that result from the nonlinear interaction. And then there's a term, order gamma term, which results from the presence of this non-homogeneous term in the equation, which is the beta gyre effect. And then there'll be an order beta term as well, which I didn't show here, plus the complex conjugate, because all the solutions have to be real. And so the order alpha terms end up having powers of t, meaning they increase with time, which would mean that we would need to work out a late time solution using the process of multiple scaling in asymptotic analysis. The order gamma term is what we are interested in. It has a factor of r, so you might say, oh, that's a problem, because if r goes to infinity as we move outwards from the center of the vortex, it could mean that this term would be going to infinity, but it doesn't, because it's multiplied by that. And the omega of r, omega bar goes to 0 because the vortex flow decreases and goes to 0 as r goes to infinity. So when omega r goes to infinity, omega bar goes to 0. So this becomes 1, and then the whole thing becomes 0. So this term does go to 0 as r goes to infinity, which it should be doing. It wouldn't make sense to have anything that increases or that does not go to 0. And so this term here, e to the I lambda times e to the minus I omega bar r times t, written like this, represents a rotation in the counterclockwise direction, because omega bar is real. It's real and positive. So it means there's a wave with a speed of omega bar r, which is added to the nonlinear part of the solution and the linear solution. And so, and these are terms shown in blue are the effects of the nonlinearity. I didn't show what they look like, but they are very complicated and were evaluated explicitly in my student's thesis. And if we include higher powers of epsilon, we'll get higher harmonics, as I said. And the order beta term appears at higher order, so I didn't show it here. And then if we solve the Laplacian of psi equal to psi, would get our stream function. And so this is what the order beta term looks like. The beta, it has a wave number of 1, so we've got like two dipole kind of structure. And finally, I'll just show some pictures that I got from doing numerical solutions. So after my student finished his master's thesis, since then we've been doing numerics as well. So the same formulation that we just set up, in these pictures, the wave number k is 2. So that's why we see two blobs of blue. So like positive, negative, wave number of 2 within our interval from 0 to 2 pi. Small parameters. This is the initial profile. And at later time, we have a situation like this. If everything is linear, then we'll just have a wave going out like this, which you can see symmetric in lambda. But the beta gyre effect, the addition of the beta terms, means that there's an asymmetry added on top of that. And so if we consider a case where the beta gyre effect is small, so gamma, which was beta over epsilon, is small, really small, then it's added on top of the dipole structure, is added on top of a picture like this. But if it's much larger, large in this case is 0.01, then the beta terms dominate to the linear terms, and we have a structure like this, which is like what we saw in the analytical solution. And it turns out that this is a good representation, which this is a good representation which is consistent with observations of the beta gyre. There is this additional secondary spiral motion with a dipole structure, which in real life causes the movement of the hurricane. So I'll end just by saying that there are many other wave mean flow interaction problems of interest, and these are some others that I've looked at with other students in the past. Topographic gravity wave packets. So topographic waves are the ones that go up above the mountain and might affect, break and result in turbulence. And then a more recent case where I looked at, my student and I looked at large-scale Rossby waves in 3D with gravity waves, and where the two types of waves interact. And in each of these wave studies, we our results could help to improve the representation of unresolved small-scale waves in large-scale models. So I'll end there. Thank you very much for your attention. I think I may have gone a few minutes over time, but I'm happy to answer questions now.
Okay, thank you. Thank you for that very interesting topic you have. Why am I doing that video? Can she still see me? Because I can see her. Prof, can you still hear us?
No, I don't see. I see some people. No, I don't see anyone. Any of you? I don't see you yet.
Maybe it's because I'm in the dark.
Yeah, I just see. For now, I don't see anything.
Do you see me now?
No, still not.
Okay, something went wrong.
Yeah, I think your video. Yeah, now I see you now. Yeah, now I see you.
That's good. Thank you.
Okay.
Yeah, thank you for that interesting talk. I don't know if we have any questions, perhaps from the floor, from the room here. Any questions? Do we have any questions online? There's nothing in the chat yet. So I wanted to find out, Prof, apparently there's a difference between a hurricane and a cyclone.
Yeah.
And if there is that difference, how would your equations change so that then we are looking at a cyclone instead of a hurricane?
Yeah, so so I'm just sharing my screen. I think you can, yeah, I'm sharing my screen again. So the hurricane, so what it is a cyclone. So hurricane is a specific type of cyclone. So a cyclone in general is the term that's used just for the system of rotating fluid flow with sustained winds, so meaning continuously rotating. So that's like the angular velocity that I called omega bar. I had it just as a function of r, as opposed to maybe something that changes with time. So it's fixed and it continues to rotate at a high speed. And a tropical cyclone is when a cyclone occurs in the tropics. And then in that case, the thing that generates the cyclone, the mechanism that generates it is heat over the ocean. But as opposed to a cyclone that might be generated in some other context, which might come from some other reason. And then a hurricane is specifically a tropical cyclone with very high maximum wind. So it's a special type of tropical cyclone. Now, tropical cyclones are called hurricanes when they occur in the sort of Caribbean Sea and Atlantic, go up into the North Atlantic. In other parts of the world, they have different names. So like they're called typhoons, for example, I think in some parts of Asia and so on. So depending on where it's occurring, it might have a different name, but that's like a specific case of tropical cyclone. And then, the context in which the vortex-Rossby waves play this role of affecting the eye wall structure and the beta drift and all that is when the cyclone winds are very high. Now we could do a similar thing for what we did in our analysis, but let's say I was considering a cyclone, but I was thinking the speed is not very high, so a weaker cyclone. Maybe I could still use these equations, but I could say now maybe the omega bar is also small. So to have high winds, I'm saying omega bar, the background flow is high compared with the waves, and the waves are a small perturbation. But what if we have a weaker hurricane or a weaker cyclone where omega bar is small? Maybe I could put a small parameter here and say that's also small. Then in that case, all the terms that have bars on top would be small terms. The beta effect would be smaller, but maybe non-linearity would be greater. Right? So in general, once I've set up things in this mathematical model, I can decide what physical phenomenon I want to study just by changing the relative magnitude of different terms and so on. So that's a general thing we can do. Or we can say, what if we have higher amplitude waves? In that case, where epsilon is no longer small, but it's order 1. Then now if this is order 1, it means these terms now dominate. So I can no longer say a perturbation expansion where epsilon is at higher order. The epsilon would be right there at the leading order, right? So I can study we can study different phenomena by just changing things within our model. That's the power of mathematics.
Okay, thank you. I'll take the question. Before I go there.
So I see a question in the chat.
Yeah,
and then also someone asking to unmute and ask a question.
For now, this one on the floor here, we'll take this one first. So maybe you should come here because there's a microphone.
Hi.
Yeah, hi.
So I wanted to ask a question regarding the waves on the ocean. So like in the case of offshore wind turbines, how do waves affect the energy production in those wind turbines?
Okay, yeah, so that's a good question. So I haven't looked specifically at that problem, but any situation where there is like we are looking at waves or the airflow over the ocean, there is a coupling between the atmosphere and the ocean. So, and the coupling takes place on the interface. So whatever is going on in the ocean, like storms and so on in the ocean, would affect the atmosphere, and the same, there'll be feedback between the two sides. So if we are trying to generate energy from the atmosphere, like with turbines in the atmosphere, that means that whatever is happening in the ocean will affect the atmosphere, which will then affect the energy that we generate. And or if we have turbines in the ocean, then obviously there the ocean will affect whatever the amount of energy that we are going to generate. So if we want to get some use mathematics to get a better understanding, maybe how best to set things up or where to set our turbines so that we can get maximum energy generation or something, where maybe are the highest waves so we get more energy and so on. We can do a mathematical study where we could have maybe a coupled system, so like atmosphere and ocean coupled, and then have to do some matching, asymptotic matching at the interface, and then maybe do numerics as well. In fact, I have a student right now. In fact, the student who did the thing on the vortex Rossby waves now is doing his PhD, and we are looking at coupling between the atmosphere and ocean. So it's a much more complicated problem, but at least maybe we can get some insights that would help in situations like what you described.
Leroy?
Leroy, do you want to unmute and ask your question?
Yes, good morning. Very great presentation, Prof. Thank you so much. It was quite informative and engaging. So my question is on the perturbation methods that you were using, where you took the first terms and then you solved that problem, substitute it back. My question is, do you use any software to sort of solve that system, or you use rigorous analytic methods? That's my question.
Yeah, so the when we are doing the asymptotics, so we will have something like this. So we have our solution in powers of the different parameters and so on, and then we plug it into our equation. So at leading order, we'll just have a simple linear equation. So the leading order, which will be the terms with the superscript of 0, would go in here, and we'd have just a straightforward differential equation. Well, it's not that simple, but it's fairly simple to solve. Psi 0 here, and these are the terms with the bars are known, so it would be a non-homogeneous equation, and we could solve easily. So we don't need any special software for that, given the initial conditions we have, which we've set up to be some well-defined function, and it becomes just a simple linear mathematical problem. Now, at the higher orders, the problem is not that complicated, because each time you plug in, when you plug in your different terms and separate them out into different orders, each equation has the linear differential operator, this on the left-hand side, and then on the right-hand side is whatever you've got from the earlier orders. So we can usually work those out by hand, except that they get complicated. So like we got all this stuff here, but we've got all this explicitly. Now we could, if it gets too complicated, we could use something like Maple or Mathematica to help with the analytical work. But then when we get to the numerics, if we want to do a numerical solution, then now we use kind of standard numerical methods like pseudospectral methods and finite differences and so on. And with the numerics, usually I just write code from scratch, because there's no one software that really works for these specific problems. So I write the code from scratch, and when I have students doing it, they also do so. And then we use the information we got from the asymptotic analysis to give us an idea of what the numerics should be doing in order to validate our numerics.
Okay, and are these methods, obviously some of these methods are prone to some error. How do you counteract when you engage that kind of error? When you
exactly.
Look at yes.
So for the numerics, well, of course, we have to pick methods that are suited for our problems. So for example, in my case, where I generally, or in a case like this, where I'm studying wave perturbations, as I said earlier on in the presentation, the waves can be represented by Fourier modes. So the spectral methods which are kind of spectral and pseudo-spectral methods, which are kind of standard numerical methods, can be used where we are basically representing the wave in this form, taking a Fourier transform of our equation. Now, these are of our equations. Now, these are well-known methods, and we always do an error analysis before we begin. Now, in a nonlinear problem, we may not be able to have an exact representation of what the error would be, but we can get an estimate at least. So we know what order of magnitude of error we are expecting, all the different types of errors we are expecting with the particular method, and so on. And then also we can validate our results by having obtained, done the asymptotic analysis beforehand. So yeah, numerics are a whole separate talk. I could talk for a couple of hours just about the numerics, but I just chose not to go into detail in this talk.
Okay, thank you.
Thank you, Leroy. I believe there are 2 questions on the charts.
Okay, so the first one, maybe I can read out the questions. I can read out the questions I see in the chat. So I see a question from Campbell. How do you determine which waves were generated by gravity versus those that are an interaction of different air currents? The ripple type effect appears to be generated by both. And yeah, so how do we distinguish between the different types of waves? So I don't do that. That's not part of the research I'm doing in the real atmosphere, because I'm not going out and taking measurements. But those scientists who measure waves have many different techniques for measuring waves, taking measurements and then doing analyzing. So this would involve statistical kind of analyses to isolate the different waves that occur. Because of course, as you can see from the mathematics, there may be different things going on at the same time, and nonlinear interactions, different wave modes. And so mathematically, we can do it really cleanly. Like these waves have this, scale, and these waves are like e to the ikx, and these waves are e to the 2ikx. So we see them separately. In the real atmosphere, of course, that's not going to happen. It will be a wave packet with waves with different wavelengths, different wave numbers. So, but they are able to use statistical analyses to isolate the different types of waves. And then based on the properties of the waves that are observed, they can see which waves have the properties of gravity waves or other types of waves, which some others that I didn't even mention, and then kind of classify them. So that's a whole research subject on its own, which I don't get involved in, but I do see the results of their analysis in the published work showing the different types of waves. And some waves are of different scales, like internal gravity waves and planetary Rossby waves are on completely different scales. So we wouldn't confuse those, but they both affect the background mean flow. And so in the end, they do have some interaction because they are both affecting the mean flow and being affected as a result. So that's also another very complex problem. Now yeah, so I hope that, I don't know if that answers your question. So the short answer is it's very complicated, but it can be done.
All right, thank you.
Yeah. So there was another question in the chat, if you would like me to answer that.
Yes, please.
So Kutsang says, I have 2 questions with regard to internal gravity waves generated by a mountain. Which boundary conditions can be used for this problem? And does the critical layer occur after the upper boundary layer? Okay, yeah, that's a really good question, which I've actually done lots of work on internal gravity waves. I just chose to talk about vortex Rossby waves, but I've done lots more work actually on gravity waves. So with the gravity waves over a mountain, let me see. Maybe I'll go back to one of the picture, if I have a picture where, yeah, let's say, let's go back to this picture because I don't have any graphs for my gravity wave papers. So the way I would set, if you want to set things up mathematically to study internal gravity waves generated by topographic waves, what you would do is the simplest model would be if you want to try and do it, it's a 2D study, so you can do asymptotics first, and then afterwards maybe you can make it more realistic to do numerics. So if I wanted to do a 2D study, I could say this is my 2D rectangular domain. But now instead of saying like what I did with the beta plane where I said horizontal plane, now it's a vertical plane. And so I have let's say the X coordinate is horizontal and the maybe Z coordinate is pointing out from upwards, the altitude. So now I'm on the Earth, and I'm taking some region going in the X direction, east-west direction, and then a coordinate pointing outwards. Now I can only do that if my region is small enough, small scale, so I'm ignoring the curvature of the Earth. So that would be the simplest 2D model. Now I can just say I have a lower boundary condition, which is this. I put in a lower boundary condition, which represents this. So instead of the case I did where I said the vortex Rossby waves were generated by some initial perturbation, this time I'll set it up as a boundary value problem where let's say initial boundary value problem where maybe my initial condition is 0 everywhere. And then at time t equal to 0, I introduce a lower boundary, which represents the form of the wave. The form of the mountain, like this. So I could do like a Gaussian thing, like again, like maybe e to the minus x squared or something to represent this. Or if I want a mountain range with many peaks, I could do like e to the minus mu squared, e to the minus x squared multiplied by an oscillatory function like cosine. So then I would have oscillations which are decreasing as we go like that. Then in that case, I would have a mathematical problem with the waves generated by the lower boundary condition. I've actually done quite a bit of work on that problem. That was the problem I looked at in more detail in the past. And then more recently, I've been looking at vortex Rossby waves. And then in that case, the critical level and the waves will go up and they get to the critical level that I talked about, and it would be like some level where the wave phase speed matches the background flow. And then we might have wave breaking and things at that level. And mathematically, we can do matched asymptotic expansions where we have an outer solution, and then around the critical level, we do an inner solution, and then we match, do asymptotics to match. So these are kind of interesting mathematical problems. I didn't get the chance to go into detail on all that, but that's how we can study gravity wave critical layers. There's a very huge literature on that topic, and if you look that up, you'll find I have a few papers in that area.
Okay, thank you. Do you have any other? All right, we have one last question from Alice.
Hi, Prof. Thank you for your talk. I wanted to ask about the relationship between planetary Rossby waves and vortex Rossby waves. Is it just the vorticity that connects them and makes them both Rossby waves, or even though their length scales are quite different, is there more similarity, and is the Coriolis force involved in vortex Rossby waves?
Yeah, so in the case of planetary Rossby waves, the main effects that generated or cause the waves or the main effect that generates the waves is a mechanism based on the Coriolis force, so the rotation of the Earth itself. And they are on a large enough scale that the rotation of the Earth affects them directly as a primary effect, as opposed to the smaller scale waves, which of course, anything that's smaller scale, the effect of the Coriolis force will be smaller. We are standing here on the surface of the Earth and we don't feel the rotation of the Earth. Of course, it's affecting us, but it's not a primary effect. But imagine that you are standing here and you're also standing here on the surface of the Earth, and you're also spinning on like a kid's, like a merry-go-round or something like that. So while you are spinning, of course, that's the effect you feel. The effect of your own rotation will be much greater than the effect of the Earth, the rotation of the Earth. In my analysis, the rotation of the Earth is included in the beta term. So it's a small the rotation of the vortex has a greater effect on vortex Rossby waves. But the rotation of the Earth in the end also plays a role in the development of the vortex Rossby waves. Surprisingly so, like more than we might have expected. And that's where this beta drift comes about. So now, the planetary Rossby waves, which are affected mostly by the rotation of the Earth, are on a large scale, and the vortex Rossby waves are like just a small thing taking place within your vortex your hurricane or your cyclone on the surface of the Earth. So the two types of waves might not directly interact because they are on different scales, but the way in which they might interact would be if the vortex Rossby wave in the hurricane affects the background circulation in that local region where the hurricane track is, then that can affect, affecting the background flow means that it might have some effect on the large scale waves as well. So in the end, the waves of different scales, like Rossby waves and gravity waves, or planetary Rossby waves and vortex Rossby waves, can indirectly influence each other through the background flow. Since they are both feeding into the background flow is also affecting each of them. So indirectly, they can all interact. And that's mathematically, we'll look at it as a nonlinear problem. For the people who are going out and taking measurements, they will look at it as being the weather, local, smaller scale effect affected some longer term effect, like the larger scale flow. So they all interact with each other, but just on what orders of magnitude. That's how we see it mathematically.
Thank you. All right, thank you. Are there any other questions? No? So there are no more questions, but as you can hear, you need to come.
Oh, okay, okay, yeah, okay. So I see in the chat, somebody says, please come back and talk about the numerics. So I'd love to hear more about it.
As well. So I was just making sure you read that.
Yeah, I've opened up the chat now. So yeah, so numerics, as I said, numerics is a whole other topic. So as also the details of the asymptotics for any math people who want to know about those. I chose to talk mostly about the geophysical fluid flows and what the different types of waves and so on, without going into detail on the mathematics or even talking about the numerics at all. In general, I do the different things and I kind of try to put them together. I have students in some students doing numerics, some who prefer to do analyses. PhD students, usually I make them do both. And I go to math conferences and also to atmospheric science conferences. So then I kind of tailor my talks depending on the audience I'm talking to. So I can talk about numerics as well.
All right. No, thank you so much for your talk, and we hope we'll be engaging with you some more.
Oh, okay, yeah, thank you very much for organizing this and for inviting me. I hope that all those of you in the chat, in the online and in the room as well, I can't see those of you in the room, but I hope you've had enjoyed the talk and have learned a little bit about whatever aspect you didn't know about already. I know there are some math people in the audience and maybe some atmospheric scientists. So some of you probably are already familiar with some aspects of what I talked about. But I hope you were all able to get something out of the presentation.
Yeah, all right. Thank you so much. Thank you.
Okay, thanks.